Welcome to today's mini lecture. So, first of all, in the past 2 weeks, we've been talking about the periodic table. We've been talking about its layout. We've been talking about the metals versus the nonmetals. Well, we also looked at the trends. We talked about how to determine the valence electrons and also how to determine the oxidation numbers. So, the next step is let's start putting all of that together and let's start looking at chemical bonding. So, big things. Why do any of the elements bond together? The simple answer to that is to become more stable. Now, in chemistry, you're going to hear me talk about the magic number of 8. So when we looked at our valence electrons, they started and they 1, 2, 3, 4, 5, 6, and we got all the way over to the noble gases and had 8 valence electrons. That is the most stable structure that you can have. So what we're going to do is we're going to look at different ways to reach this 8. So we have 3 types of bonds whenever we're talking about chemistry, and they're all based on the different types of elements. So if I look at the periodic table, I see my stepping stone here. All the elements to the left of the stepping stone are going to be classified as metals. They all are going to have 1, 2, 3 valence electrons. They're all going to lose those valence electrons, and they're all going to become positive ions. We call them cations. Over here, we have all the nonmetals. Not nearly as many nonmetals, but they carry a valence electrons of like 5, 6, 7, and they will always gain electrons, so their overall charge is always going to be negative. So the first bond that we deal with is called a ionic bond. What is an ionic bond? Well, it's going to be a positive metal that bonds with a negative nonmetal. Now, how does this bonding take place? Well, I like to look at it like this. Let's say that I take sodium. Sodium on the periodic table is number 11. It's in the first family, so it has 1 valence electron. So I'm going to allow this pen to represent the 1 valence electron. Now we're going to try to bond sodium with chlorine. Chlorine is number 17, and it's in the halogen family, and it has 7 valence electrons. So I have 1, 2, 3, 4, 5, 6, 7 on this side. Well, in order for chlorine to become stable, it has to gain an electron. In order for sodium to become stable, it needs to lose an electron. So I'm going to put these in other hands so it actually matches up. So now I've got the chlorine on this side, sodium on this side. So what happens is when they start getting closer to each other, the atoms, those outer electron shells get real close. We talked about electronegativity, and we know that elements further to the right of a period is going to be a lot more electronegative. That means they want to pull that electron away. Elements further to the left are going to have less electronegativity, therefore holding on to that electron a little bit less, so it doesn't take as much energy. Now what happens is, here they get closer and closer. My chlorine wants this electron. My sodium wants to get rid of this one, so it gets right here and doop, exchanges. But as soon as that electron is lost, my sodium becomes positively charged and my chlorine becomes negatively charged. They're so close together because their energy levels have to get almost touching that now they are connected. It's called an electrostatic attraction, magnetic, like opposite poles of a magnet attract. Guys, that is an ionic bond. Well, a molecular bond or a covalent bond is going to be very similar, except this time, let's say that I have different elements. Sorry about that, guys. I have different elements, and this one has 7, and this one has 1. But this time, I get to it, and they don't try to take one enough away from each other. They just say, you know what? I have 7, you have 1, you have 1, I have 7. What if we allowed And we got close enough to allow all 7 and 8 of these electrons to go around both our nucleuses and becomes the outside energy level for both the nucleuses. So what you just did is you had the sharing of the atom. When you have sharing of atoms, there are no charges, there's no positive, there's no negative, and what ends up happening is all covalent bonds are going to be elements that are nonmetals, and it bonds to another nonmetal. So you end up getting electrons shared, but still, the magic number in chemistry is 8. So the last bond that I want to talk about is a metal or a metallic bond. Yeah, you can figure that one out. It has some transition metals in it, and it's at least going to be made up of 2 metals. So it's a metal and a metal. Now, you remember those d orbitals that held 10, right? It had 5 rooms in it. Well, those are big orbitals. So what ends up happening is when you get 2 metal atoms that get close together, the d orbitals overlap. And you get what's called it's like a sea of electrons. They just float, not just in that one, they overlap in all hundreds, millions of these atoms. And the electrons on the outside are not now dedicated to this nucleus or this, they just float around. And by that huge sea of electrons, it holds all of those metals together, and that is called a metallic bond. Well, I'm going to shrink this down just a little bit, and I want to talk about the notes. All right, good job. So we're going to talk a little bit about the notes. I need to talk about the different types of bonds. So we said ionic bond was a metal and a nonmetal, and we said that it is going to be the transfer, or whenever you have electrons being lost or gained. You always are going to have an electromagnetic attraction. Now, what are some of the characteristics? This is some of the things that we have to make sure that we know. So as we come in here and we look at this, you can see that, number 1, they are not true molecules. Why? Because they don't have any sharing of electrons. They make crystals. So whenever you see crystals like salts and different ionic compound crystals, that's what it is, that repeating pattern. Also, if you place them in water, they're always going to dissolve. So ionic compounds dissolve readily in water. So also, if you get them hot enough, they will melt. Now, if they're dissolved in water, or if they're in their liquid form, because they have those positive and negative ions all the way through them, they conduct electricity. Electricity, very simply, is nothing more than the flow of electrons. So if I have positive and negative ions everywhere, those electrons can just go all the way through. All right. Most all of your ionic compounds are going to have really, really high melting points. That means that in order to get them to turn into a liquid, you're going to have to put a lot of energy into them. Generally, they are brittle, kind of like peanut brittle. You've probably eaten peanut brittle, right? It can be kind of, when it warms up a little bit, it can be kind of firm like Play-Doh, but if it cools down, it just ching and shatters. That's it. And then finally, we often refer to them as salts. Now, we have a chart that actually looks at electronegativity, and those electronegativities, that can be found on a periodic table, but instead of it listing like masses and atomic numbers, it just lists electronegativity. But guys, honestly, I gave you this just so that you could see that you have what is called true polar or covalent compounds, but most of them are just kind of they don't have all the characteristics. Just like with ionic compounds, some of them are just kind of, they don't have all the characteristics, because there's a big leeway of difference. All right, so what I'd like to do next is I would like to talk about the covalent molecules. So guys, if you're getting tired of listening, I'm talking too fast, this would be a good time to hit the pause, take yourself a break, go get you a glass of water, come back in. and then we can start back. All right, welcome back if you just came back in. I know it looked like a short break, but you could pause it as long as you wanted to. We're going to talk about some covalent compounds. These are molecules, and this is going to be composed of a nonmetal and a nonmetal. Key term here is you have the sharing of electrons. There are no overall charges, just the sharing of electrons. Whenever you have two electrons being shared, one electron from this element, one electron from this element, you have what is called a single bond. And that's going to be, you have two electrons being shared, and we say it's one shared pair. Now, sometimes you have two electrons from this element and two electrons from this element. So you'll get a double bond. And then every now and then you'll get three electrons, and they're called a triple bond. So you have single, double, and triple bonds. Now, guys, it's pretty much common sense. Which one do you think is going to be the strongest? Right, the triple bond. The single bonds are going to be long, and if you like to think about it as a stick, you go out in the woods and you find you got a long stick. It's about like that. You can just take it and break it over your knee, no problem. Well, if it's a double bond, what it does is it's a lot shorter. So you take that same stick and it's like this, a lot more pressure, but you can still break it. But a triple bonds, they're real short. You have a stick like that and about that, are you going to be able to break that? Probably not. Triple bonds are the strongest of all the bonds, and they do contain the most energy. Now, covalent or molecular compounds will not form crystals, but they will with one exception, and that's diamonds, or one that we really know of, and that's a diamond. Carbon-carbon molecules that pack on top of each other, forming a crystal lattice. That forms diamonds, but you know that it takes a tremendous amount of heat and pressure and energy and time in order to get that diamond to form. If you have a molecular compound, you're going to have compounds that have low melting points and boiling points. They're usually going to be called very volatile. Like if you think about gasoline, you can smell it. That's because it evaporates very quickly. The reason that it evaporates quickly is because it has a very low evaporation point, or going from a liquid to a gas. So that is volatility, how quick it changes from one substance to another. So molecules and covalent compounds, they do not conduct electricity. So the last that I want to talk about is going to be our metallic bonds. Metallic bonds are going to be metals, and they have to contain at least one transition, but most of the time it is two transitions. But what happens is, you can see there is no gaining or losing, there is no sharing, you just have a free-floating sea of electrons and all of those overlapping d orbitals, because they stick out everywhere, all of them, so it just floats around. It's kind of like a honeybee. If you think about a honeybee box and a honeybee box beside of each other, there's bees everywhere, but at the end of the day, the bees from this one are still in that box, and the bees from this box is still in that box. They don't change over, but during the day you can see bees just everywhere. All right, as we go back in, you can see that they are going to be good electrical conductors, right? You can look up here, copper, definitely. That's why we use it in all of our copper wiring. It's inexpensive, and it's a good conductor of electricity. They have very, very high melting points. So think about metals, right? Common metals like iron, copper, they all have to have a tremendous amount of energy to go from a solid to a liquid. So let's just have a quick recap. There are three types of bonds. There are the ionic, the molecular, and the metallic. An ionic bond is going to be made of a metal and a nonmetal. A molecular bond is going to be made of two nonmetals, and a metallic bond is going to be made of two metals. So there are key words that you need to make sure that you pick up for each one. So what I think, with the help of this set of notes and this video, you should be able to go through and answer all the questions on our concept questions. That's our next activity. All right. Thank you. I want to tell you how good a job y'all have been doing, and I look forward to our next meeting.